Welcome to this video on Coulomb's law and vectors. And in this video, what we're going to do is take a look at how Coulomb's law can be used for more complex situations than just having two charged objects like we had before. Let's just make these both positive, and they're going to repel one another. And the strength of the repelling force we found out was equal to this quantity, K times Q1, and there's the absolute value, times Q2 over the distance that they are separated squared. And it's kind of boring just to plug and chug, right, in these cases. And so here we have a scenario where we have four charges set up. And we're going to look at the method, which is really just a vector analysis and vector summation of how to do the scenario. But it's important to look at, so we'll take this time to do it. So it says that four charges are arranged in a square with sides of length 2.5 centimeters. And the two charges in the top right and the bottom left corners have a positive 3 times 10 to the negative 6 or 3 microcoulomb charge. And the charges in the other two corners are negative 3 microcoulomb charge. And they want to know what is the net force exerted on the charge in the top right hand corner by the other three charges. Okay, so when you think of a situation like this, of course, as things push away from each other because the distances are changing, the force will change as well. But we're going to say that that first instant where they're 2.5 centimeters apart, or perhaps I have them attached at these edges, and so they're still pushing and pulling on one another. So what we're going to do is we're going to just independently describe the different forces that are acting on this charge. So basically, I'm going to look at it from the perspective of this charge. So this charge is getting attracted, right, to this. Well, they're really both attracting one another, but we'll say it this way. And the same thing's happening over here. Now, because these have the same separation distance and the same product of charge, right? So they have these same, everything's the same. They have the same force, okay? Which let's just denote with two little hash marks, okay? And I'm going to call this one electrostatic force 1, and I'll call this one electrostatic force 2, although they're the same value, okay? And then this one over here, that's the positive 3 microcoulomb charge is going to repel this one, right? But the arrow should be slightly smaller. And the reason for that is that it's slightly further away, right? Because this is a hypotenuse or a diagonal, which means that it's a greater distance. So if I go ahead and just change this to meters, and we'll go ahead and compare those, this would be 0.025 meters. And if you actually do the Pythagorean theorem here, so 0.025 squared plus 0.025 squared, the square root of that, you get 0.03536. So it's a little bit further away, and so it doesn't have as much impact on the repulsion. So I'll put 1 there, 1 hash mark, just to show that it's less, but it's not half, right? So just don't take that too literally. Okay, so now that we know what's happening here, oh, and I need to label this, and we'll label it FE3. So I'm going to draw my force diagram here, and I'm going to show that these two are pulling it in either direction. I'll label that FE1, FE2, and this one's pushing it, which is FE3. Now I know that in order to find a net force, right, it's really the sum of all the forces that are acting on the object. And when we do vector addition, right, we have to sum things that are in the same dimensions first before we can find resultant values. So in other words, what I need to do is I need to find a net force in the horizontal and the vertical dimension in this case, or parallel and perpendicular. Now what I'm going to do for ease of description is I'm going to write y as my vertical and x as my horizontal, just so I can use some subscripts. So I'm going to say that these are the two values we're looking for. Now, right off the bat, I can say that this is a negative x value and this is a negative y value, right? So this is vertical only and it's pointing in the negative y direction according to my legend, and the x is pointing in the negative direction according to my legend. But the F3 is pointing neither in the x nor the y, but both, right? So it has a component that I'm calling F3E, FE3x, which is positive, and it has this other component, which is FE3y, which is also positive because it's pulling up. So to the right and up, and so we can see which we have in each dimension. Now what I need to do is I need to sum up only the x part. So I'll go ahead and put the positive one first. So I'm just going to take away the e for now. So F3 in the x minus F1, and I don't have to write the x subscript because it's all in the x, and that equals the net force in the x. Net force in the y, okay, we have F3 in the y minus F2. Okay, so we've got these two values. Now, in any vector addition, once I've got a total x component and a total y component, I can add these two together into a third component, or a resultant component, which would be the square root of the x component squared plus the y component squared. And that will give me the final magnitude, okay? And then I can find the final angle that that force is directed at with, I mean, any inverse of sines, but maybe inverse tangent of the y over the x. And that will give me a final answer of magnitude and direction. Now, in order to actually put numbers in this, what I need to do is figure out what F1, 2, and 3 are in order to even do that. So when I look at these, I can just independently calculate the combinations, right? And so I see this interaction here is described as Fe equals K times the absolute value of, I'll call this Q1 and Q2. It doesn't really matter which is which because their signs don't matter, divided by the distance squared. And I'll repeat that same process for all the components. Now, actually, I pointed to these two, which was silly. I should be pointing to these two and to these two, right? So this is the force between these two, but it's also the force between those two. The one in the middle, however, this one, that's going to have a slightly different expression, although it's the same setup, but the R value will be different. So let's go ahead and calculate F1 and F2 because they're the same value. Okay, so if I was putting these values in here, I'm going to have, and I'm writing it in microcoulombs, even though I know I would need to actually write it multiplied by this, right? It's just to save space. So over here, I'd have 9 times 10 to the 9th, which is the K value, times 3 microcoulombs times 3 microcoulombs. I could have done 3 squared. And then I'm going to divide by the distance they are separated, which was 0.025, and that is squared. And I believe that that value is going to come out to be 129, if I did my calculations correctly, 129.5. So essentially this one and this one are the same. And then this one over here, what I've got to do is the same calculation for the numerator, 9 billion times 9 microcoulombs, divided by, and now I'm putting in my 0.03536 squared. Now, I've got this value and I've got this value right off the bat because they're all x or all y. But this one and this one, these ones don't equal whatever this comes out to be, which I think is 64.7 newtons total. Okay, so what that means is I need to first break this apart, right? I need to get the x component and the y component. And if you recall, the way that I do that, make a little bit more room here, is say, I'll do it this way, f3 in the x is equal to f3 times the cosine of the angle if I'm using this horizontal angle, and f3y would be f3 sine of theta. Now in this situation, because this diagonal bisects the corner, that's 45 degrees, right? And that would be the same thing right there. So I don't have to do the calculation twice because it has the cosine and the sine of 45 degrees are the same thing. And so I can put 64.7 times the cosine of 45 degrees and 64.7 times the sine. And these two values are what I will add. Now you can see what's going to happen in terms of the direction is that this number is smaller than F1. And so what's really going to happen to this, the net force direction, is actually going to pull back this way a little bit, which is weird because you'd think of this as repelling. But all that's going to do is because these two are closer and therefore exerting more force as this pulls, it will just have a little bit of resistance from this one. So I won't go ahead and plug all the numbers in here because you can do that algebra on your own and the arithmetic on your own. But the setup is what's most important. And in subsequent videos, what I'm going to do is take a look at other combinations when we look at electric field, other shapes, because it's still vector addition, and we'll do a little bit more practice with that later.